Devaney, and I'll be talking about all-optical switching MRAM. Now, that's a very big field, so we'll restrict it to a very special case, helicity-independent all-optical switching, and particularly one case of that, because there's two that are generally recognized in literature. So what is helicity-independent all-optical switching? So let's decompose that. Helicity-independent means that the polarization of the incoming light does not matter at all. It's not a factor. So it's a process under which a very fast pulse, or sometimes referred to as an ultra-fast pulse on order of femto to picoseconds, can cause the magnetization of a ferromagnet to switch from one state to the other without using an externally applied magnetic field. So this was first discovered in transition metal ferromagnetic alloys like GFC, that's gadolinium, iron, cobalt. I'll just call it GFC from now on. There's other materials that it's shown up in, but I'll be mostly focusing on GFC today. So in this regime, with this ultra-fast pulse, the ferromagnet temporarily enters a ferromagnetic-like regime, which allows for the switching behavior. It also only happens in uniaxial systems in uniaxial anisotropy. But also, it's fundamentally a thermal process, but simply it's called all-optical because usually the way you apply the thermal excitation is just with optical methods. But in theory, another way could be used, like let's say you want to excite a mechanical transducer with a laser, which then gives the thermal excitation. It just happens that lasers are pretty much one of the few ways you can get these ultra-fast pulses. So when did these first start coming up? So the experimental observations first showed up in 2011 in gadolinium and iron. So you see on the right here is an experiment where they had a laser with a laser fluence of 4.4 millijoules per inverse centimeter squared at 83 Kelvin. So that's pretty cold, below the compensation temperature. So the switching was caused by a 60 femtosecond laser pulse with a photon energy at around 800 nanometers. So that's just right outside the optical spectrum and then very near infrared. So you can see here that the pump probe delay, so at zero, we have the 60 femtosecond pulse. Then within around 1 to 2 femtoseconds, this magnetization measured by XMCD switches from negative 100 and 100 to their opposite states. So that's very fast switching. So let's talk about the starting temperature dependence of this system. So the switching pulse threshold duration has a very linear dependence on initial temperature, surprisingly. So let's see here and here. So as your temperature increases, the necessary pulse also decreases as it increases. And you can see this in both of these charts here. So there's a Pareto front under which, where if your starting temperature is below and your pulse duration is below, you'll get that switching behavior. On the boundary, you'll get a mixture of that demagnetization and switching behavior. Then outside of it, you'll only get demagnetization. So there is a boundary where you see these two behaviors kind of intermixing. So you generally don't want to be right on the Pareto front. You want to be kind of deep into it. And just for vocabulary, compensation temperature is the temperature in which sublattice magnetizations cancel. So usually in ferromagnets, you have two sublattices, which you can treat somewhat separately. And as I said earlier, MRG has a slightly different approach here, a slightly different mechanism here than GFC. So you can see that actually if the T0 minus T comp goes above zero, actually you can't get that ultra fast switching at all. So it's a bit different. Let's talk about the phenomenological model. So the underlying physics aren't perfectly well understood, so we understand them by analogy with another model, hence the phenomenology. So it's expressed by longitudinal spin dynamics in terms of sublattice resolved angular momenta. So for this model, we require the spins of two sublattices. So let's first look at this model here. So the two green dots are the equilibrium states, and you can see on each axis is the normalized angular momenta for lattice A and lattice B normalized to the equilibrium angular momenta. So this blue region is the region that you need to start in if you want to see this ultra fast switching. If you start outside of it, when it relaxes, you will not get that ultra fast switching. So now let's look at an actual material. So here we have the angular momenta of iron and angular momenta of gadolinium. So here we see the exchange relaxation if you have a pulse on the order of greater than picoseconds. So that's fine and all, but what we actually want to see is also that block relaxation according to the block equations if you get a femtosecond pulse. So you need that interaction of both having the block relaxation and the exchange relaxation to get this transition to this temporarily ferromagnetic-like state. So this exchange relaxation always exists, but the key is to get both the exchange relaxation and the block relaxation that exists, because it needs to enter this region here to get that ultra-fast switching. In the slow limit, the slow heating limit, where you just heat the material as slow as possible, you follow this curve, and you're basically at equilibrium the entire time. So let's talk about potential applications and devices. So this is I'm not going to go too deep into the photonics talk, but this is just kind of where I was thinking. So L1 cache, it's currently well within the regime of SRAM. Classical MRAM has plenty of issues. That means that it doesn't compete with L1 cache and is mostly in the regime of L3 cache. So L1 cache is extremely fast switching and access. MRAM is usually positioned to replace L3 cache because it's seen as too slow and the access is too hard. SRAM switching speeds actually have on the order of 10 nanoseconds in around the 22 nanometer node. Faster nodes may have faster switching speeds, but since I don't have access to their PDKs, I don't actually know what the switching speed for the MRAM is. So TSMC, please respond to my calls. But yeah, there's a clear pathway to picosecond switching using 100 femtosecond or even up to like picosecond order pulses. So let's talk about potential device architectures. Let's talk about an MRAM stack with a VCSEL on top, and then an MRAM stack with large laser and a photonic selection circuit. So a VCSEL is a vertical cavity surface emitting laser, and it's a type of laser where instead of emitting semiconductor diode laser, where instead of emitting out of the side, it emits out of the top. Now you can imagine that if you're able to engineer a VCSEL with a picosecond pulse period, then you could take it, invert it, and hybrid bond it or transfer print it on top of a ferromagnet, and then use that to get that ultra-fast switching. Now, currently, engineering these kinds of VCSELs isn't really possible. Even the large-scale ones, you only really get larger scale, I should say, on the non-nanoscale. You get around 1 nanosecond to 10 nanosecond at the fastest. So it's not really super practical right now because the technology doesn't exist yet, but maybe in the future. The other one is the MRAM stack, the large laser from the photonic selection circuit. So this case, we have a very large, or comparatively very large, side-emitting laser that is easier to engineer properties in. So potentially we could have, let's say, a diode pump laser at some point on the circuit, and we could essentially direct the output using a circuit to a specific ferromagnetic MRAM cell. So this would require some pretty advanced packaging techniques. Like you need to have the silicon photonic layer chip. You need to hybrid bond it onto the MRAM layer. And that's technology that's still very hard, considering you need nanometer level placement. And also you'd have to have a bunch of advancements in photonics with the ability to control the propagation of femtosecond level pulses. So the technology doesn't really exist right now, but with improvements in understanding of metamaterials and other nonlinear behaviors and materials, it could be possible. So challenges and takeaway. So integration. Femtosecond laser integration is extremely challenging because they don't really exist at the scales we need yet. Usually the femtosecond lasers are at very large scales, or at comparatively large lab-based scales, and not integrated in semiconductor devices. So like laser technology is not there yet. Access. As with all MRAM, the complex active circuitry and potentially higher access latency and readout latency is a problem. So we need to determine a way to quickly access the data in that MRAM after we've switched it. And then the physics is still not understood extremely well. We rely on phenomenological models that have some edge cases where they don't work, like nanoparticles of early materials like terbium cobalt nanoparticles behave slightly differently. So there's a lot of stuff to still understand past this phenomenological models that's from the 80s. And then the takeaway, ultrafast switching is possible in MRAM devices and provides a potential path forward for ultrafast memories of the future. Now, of course, these are decades off probably. I'd say 20 years if we're talking about photonic engineering spans, but it certainly seems that it's a potential avenue for coming up against the L1 cache memory wall that we have with SRAM. Thank you. Any questions?